All right. We're here for AP Physics Linear Motion Problem 3, Jules Verne problem. Jules Verne in 1865 proposed sending people to the moon by firing a space capsule from a 220-meter long cannon with a final velocity of 10.97 kilometers per second. What would have been the unrealistically large acceleration experienced by the passengers during launch? Compare this value with the value determined for free fall. That's little g. So again, the idea back in 1865 was perhaps we could launch people to space using a cannon. This sort of speed, this is the speed necessary, that many kilometers in a second. That's the speed needed to launch something upward where it's going so fast that as you get farther and farther away from the planet, you're getting slowed down by gravity. But as you move farther away, the gravitational pull gets weaker and weaker. So it slows you less and less. And so this is that starting speed that you need so that you'll get launched up, but never quite come to rest. You'll keep going on out into space. It's called the escape velocity for the planet. So that's the idea behind this. So I'm going to go ahead and figure out if you were launched out of a 220-meter long cannon, what kind of acceleration you'd have to have. So it's just going to be a nice, quick kinematics problem. So here's my my cannon. We're going to fire that space capsule in. We know that we're going to go from an initial velocity of 0 meters per second here in the back of the cannon, and we're going to get launched up, accelerated up, so that when we leave here, our final velocity is that 10.97 kilometers per second. All right, I'm of course going to immediately convert that to meters per second, 10,970 meters per second. Let's see here. We know that this is going to be from front to the back here. It's going to be 220 meters, and that's what we know. Run through our kinematics. A V naught V displacement and time. This is what we're trying to find. V naught 10,970 meters per second. 220 meters. That's what we know. So we've got. We're going to do a kinematics equation with these 4 variables. That will be this one. V squared is V naught squared plus 2a times the displacement. Rearranging that acceleration would be V squared minus V naught squared over 2 times the displacement. Putting in our values, 10,970 squared minus 0 over 2 times 220. When I punch that into my calculator, I got a value of 273,502 meters per second squared, which is insanely quick. And if I wanted to, convert it to G's, right? That's acceleration due to gravity. That's 9.8 meters per second squared. How many of these would fit into there? And you end up with this being 27,908 G's. Okay, and you say, hey, that's a unit for G is a 9.8 meters per second squared of acceleration. You know that to provide that acceleration from F equals ma, you have to have an unbalanced. You have to have the outside force unbalanced of the mass times that acceleration, right? So the point is, if I had 1 G, then I would experience a force equal to my weight, right? If I'm going to punch this much in, we're pushing on these people and every object and the spacecraft itself. Everything's being pushed on with the force almost 28,000 times their own weight. Yeah, they're going to be crushed down, smushed by this, be a puddle. So anyway, yeah, this would not work. Okay, because when you have to deliver an acceleration, you have to apply a force to do that, and nothing's going to survive that. All right, that's problem 3.